Hey, welcome ladies and gents. This is this is part A of your 7.2 notes. I'm breaking it up into two parts. This is all about modeling exponential and growth and decay. So we've already graphed them and kind of got a sense of what this equation is saying, but now we're going to actually apply it. And this is some of my favorite stuff because, again, it's so applicable and you can totally see why you need it. Good news? I don't know if it's good news, but hopefully it is. A calc is allowed, so you can use your calculator on this one. Okay? Actually, you need your calculator. It's not anything you need it. Okay, so we know from the last section that this is the initial amount, that A value. Sometimes it's called a principal amount, and we'll be using that idea in the future, especially when we talk about compound interest towards the end of the chapter or the unit. B, again, is that growth decay factor. And I kind of alluded to that it's not a percent, and we're going to show how that's related over here. So it deals with the rate or percent of growth, but it's a growth factor is a little different. And then X, a lot of times I even use the letter T. Remember, variables are just whatever we choose to use, but just for the sake of being consistent with everything in this unit, this is time. But, you know, just so you know, sometimes when I teach pre-calc, I use T instead of X, just because it makes more sense. But the graphing calculators, when we use them, they use Y and X, so that's kind of why we leave it as X right here. And really, this is the end. Notice my quotes, end amount. So again, if this is a decay of a car, this is a model of a decay of a car. After so many years, the Y would be how much it's worth after that many years. Or better yet, let's talk positive. You know, you invest money into an account, a money market, let's say, over 20 years, the Y would be the end amount of your money in the account, which is always a good thing, assuming it grows, right? Okay, so let's talk about how to find the B value given the rate. And this can cause confusion, so I need to I will explain it very, very well. First thing I'm going to say is, in the real world, we always use percents in percent form, like 2%, 7.5%, you know, this test is worth 30% of your grade. We don't say 0.3 or 0.02, but mathematically speaking, you never ever use percent form when you're doing any calculation. So of course we're going to switch this over to 0.02, and this would be 0.075, but I'm just saying you're going to end up doing something else here, so let me just kind of make sure that I don't get you thinking, this is pretty straightforward. It is, but here's the thing. 2%, let's just first talk about growth, okay? 2% means your investment grew 2%, 7.5%, ooh, I want this one down here, 160% return rate or growth. But what you have to understand is the growth factor has to incorporate the original 100% that you initially invested. So that's why you're going to add a 1 to it, and the growth factor in this case is going to be 1.02. So when we are talking about that B value and you see 1.02, you know that the 1 is referring to the original amount that you invested, the 100% that you originally invested, and the 2.02 is the 2% growth on top of that original 100%. So to give you an idea here, you're going to add again that 1, and that's going to give you a growth factor of 1.075, and I'm totally going into my other spot, so this is going to be a little messy here. Actually, you know what I think I'm going to do? Let me try this a little differently, because this is going to become a mess. I'm going to try this thing right here. Okay, so 0.02 plus the 1 was equal to 1.02. There we go. That's a lot better. 0.075 plus 1 is going to be a B value, a growth factor of 1.075. And I'm going to hold off on the decay for a bit. So I noticed, I would just say, okay, do the rest of them, but percents can get a little tricky. So 0.3%, don't forget you're moving the decimal 2 places, 0.003 plus that 1, so your growth factor would be 1.003, and then 1.8 plus 1 would give you 1.8%. Oh, geez, 1.8 growth factor. And then 160% switched over to decimal form is 1.6. So when you see something like a growth factor that is really big, like 2.6, 3, whatnot, you're talking about that 100% is coming back to you plus 160% of your initial value is coming back to you. So 2.6 is a 260% growth factor, if you want to think about it that way. So so you just kind of have to wrap your head around what those numbers each mean. So down here I'll give you that trick. So you're taking your growth, whatever your growth percent is, plus your 100%. So I'm kind of writing it as a percent so that you guys can kind of understand that. So your growth percent plus 100%. So you could always just go 2% plus 100, and that's going to give you 102%, and then switch it over to a growth factor as well of 1.02. I tend to do that, but I guess what I did here is a little bit more formal or proper, if you want to get into that. Okay, decay factor. That's a little different. Okay, so when you say that something you have is now worth 2% less than it was before, what you need to think about is how much is remaining, what is left. So if you take away 2%, that means you have 98% left, and so your growth or decay factor, is 0.98. Mathematically speaking, we always just go 1 minus, again, the decimal version of that 2%, and that's going to give you 0.98. This is hugely important. I know from my own children that they start talking about this in 6th grade, sometimes in 5th grade. I know Savannah Oaks does this in middle school in 6th grade, and it's hard for them to understand, but after a while they figure it out, and it's such good practice because this is talking about those factors, like what is left versus what's taken away, you know, the whole coupon problems. So that's no different. That's exactly what we're doing here. So 0.925, so we're using those, and you know what, I'm going to stop doing all the calculations. I'm going to say here you should end up with 99.997 or 99.7% remains. Here it's 0.2. So these would be the b-values in a model that talks about a depreciation or a decay, and really you're talking about what's remaining. By the way, this isn't possible. You can't have that doesn't make sense. You can't decay more than 100%, so not possible. Okay, so again, just a little bit of a kind of a general idea is you take 1, which is 100%, minus your, and you know what, really I should even, because over on the left side I did in percent, so I'll do the same thing. So 100% minus your rate, and of course everything is in decimal form, equals what's left. And that's really important, that concept right there. So I'll keep hitting on it when we're actually doing the problems. So that is how you find your b-values, and I know that was a little obnoxious, but it really makes everything in this section much easier if you understand that. Okay, so here let's get into some problems now. It says, okay, we are in the year 2000. So in 2000, the population of Madison was 208,054 people. The population has been growing at about 0.93% each year. And what I really would highly recommend is make sure that you know what each thing is that you're looking at here. So like what does this 208,054 people stand for? That's your A value. That's your initial amount. And then it's growing at 0.93%, almost 1% every year, but that's not your B value. Your B value is going to be 1 plus that 0.0093. So again, you either have to go 100% plus the 0.93%, have it in percent form, and then switch it over to decimal, or do what I'm doing here, where put it already in decimal form and just use the 1. But anyway, so what's the exponential model for this situation? Well, the population, the end population, is going to equal the initial population, which is 208,054 people, and the growth rate, the b value, is I should not say growth rate, the growth factor is 1.0093 raised to however many years you're talking about, and I'm just using this x because that is a very general equation for this specific situation. Now you can do anything you want. You could plug in any value for x times to find the y. So in this situation, letter B, they're saying, hey, you know what? Predict the population in the year 2010. So I'm going to say, okay, my x, which is my time, is not going to be 2010 because that's talking about 2010 years later, which is not what this is saying. If we started in the year 2000, we're talking about 10 years later. What is the population? So you literally plug and chug this in. So 208,054 times 1.0093 raised to the 10th power. Now I'm going to give you the answer, but I'm going to just say this. This is not difficult. I get that. But what ends up happening is students have a hard time navigating or using the order of operations properly on their calculator. So please make sure you calculate this right now using your graphing calculator and make sure you're getting this value. So you'll hear me say that a couple times in this, especially in this unit, because that tends to happen. Notice you do need a unit because we're not talking about cows, donkeys, we're talking about people. So I could get a little bit more of a stickler and say, in the year 2010, there is a population in Madison of 228,233 people. So that is more proper. I just don't have the room to write it. Okay, so letter C, it says, when will you expect Madison population to be 250,000 people? Well, 250,000 is 250. That's not the x. We're trying to find the x. And sometimes it's not a bad idea to go, okay, that's what I'm trying to find. But the y is equal to 250,000. That's what I want to know. When does it happen? So you put that in your model. And this is, it takes a little while just to write this, doesn't it? Okay, equals 208,054 1.093 raised to the x power. Okay, so I'm going to have to show you how to use your graphing calculator with this because that's what you're going to be doing to calculate this. Until you know logarithms, which you do not know, that's the second part of this unit. And so we will solve this algebraically, but you have no idea how to yet. So what we do is we graph it, solve it by graphing. So this is a graphing problem for now. And here is really the how you use your graphing calculator. And I find that it's easier in person to show because I don't have a graphing calculator app on this. But the first thing you're going to want to do is put your equations, this one specifically, into your y1, and this equation, this whole thing, just like you're seeing it, into your y2, into your graphing calculator. So number one, and here's what I'm going to do, just because, again, I don't have a lot of space here. I'm going to get rid of that because I already told you about that, and it's in your thing. It's going to start thundering and lightning outside, so if you hear thunder, just kind of bear with me. So number one, put in y equals. Then what you do is you're going to have to adjust your windows to make it make sense. So you're going to have to adjust your windows. And I know you did work with the windows and all that in previous classes, specifically Part A, Advanced Alg, but I find that to be probably the hardest thing. Number three, then, you just hit your second button, and then what is it? In the top, it says Calc. I'm actually kind of forgetting what it says. Trace. So if you hit second trace button, which actually pushes the Calc button, then you'll see that you select intersect. And that is as easy as it is. And then you just follow what it says. It says first equation, and it asks you with a question mark, and you hit yeah, and you hit enter, and then you hit enter again, and then you hit enter again, and it'll give you your solution. Now what am I going to do? Because I don't have that, I'm going to use Desmos. I don't have a graphing calculator app on this device. So what I'm going to do is just kind of show you what I'm talking about with the whole intersection thing. So I'm going to put 250,000 right into the, actually I'm not doing that at all. I'm going to go Y, actually I'm going to go right here again. If I was smart, I would have had this done for you guys already. 250, 123,000, and then I'm going to create another equation, Y equals, the other side of the equation, which is 208,054 times my growth factor. I need to make sure I punch it in properly here. 9.3. If you don't have this, this is Desmos. This is an amazing program. I gotta tell you, I love it. And I'm trying to figure out a way that I can use it on the calculated portion so students have a little bit more user-friendly thing. But the problem is that you do need to be able to use a graphing calculator when you get into those AP classes. But anyway, okay, so here's my two graphs. Notice I can't see anything, so that's because I have to adjust my windows. I'm going to just zoom that out, and out, and out, and out. And here's the thing. I'm going to show you a trick to dealing with this situation, but you're talking about 250,000. So of course your y-axis, you're going to have this y equals 250,000, so you need to get it kind of way up there. Now I'm going to focus in on this spot right here, this intersection between the blue and the green graph, right there, and usually it shows me, there we go. That intersection is 19.84, which is how many years it takes to get to 250,000 people, 250,000 people. And that's, your graphing calculator will do the same exact thing, but if you need more of a hands-on, step-by-step, I can definitely show you when we're face-to-face. Okay, so, and I'm going to show you a trick that I use. Oops, I have no idea. Hold on, give me a minute here. There we go. Let me just put the answer first so that I have an actual answer. I'm going to get rid of that and that so I have room here. So my answer is X is going to be 19.84 years. And, you know, again, it's asking when will you expect this to happen, so you can say I expect to have, or there will be 250,000 people in Madison 19.84 years from now, or you can say in the year 1984, or I would say like in the year 2020, because if you say in the year 2019, that's really not quite true. It's not until 0.84 through the year before it's going to hit 250,000. But anyway, so you can do that, or you can say approximately 2020. That's about that year. Okay, so with that said, here is my trick, and I'm going to write it like right all over this, and then I'm going to just erase it. So just kind of bear with me. Maybe I'll bring it down here. Here's the trick, and I do this every single time because it's much easier, especially with your window. When you start with humongous numbers like this, you gotta love when a math teacher uses the word humongous, huh? Give me a minute so I can write this whole dang thing. Oh, jeez. Oops, I have student videos. That is over there. Bear with me. Oh, I need to hold on to it. Okay. It doesn't like it when I get too close to that edge. Ow, for God's sakes. X. Okay. So instead of putting these big, large numbers in, what you can do is you can say, hey, you know what? I'm going to divide both sides by 208,054. So that then, because this is really the first step to solving an exponential anyway, so you would slowly isolate your x value to solve for x. And the first thing you want to do is undo your order of operation, which is multiplication. So you would divide both sides by 208,054. Then, when I teach you, you're going to take the log or natural log of both sides and all that kind of good stuff. But what you can do here is take your 250,000 divided by 208,000-ish, and you end up with 1.2016 equals 1.0093x. So the only trick here is that you do have to extend out. Don't I would even go 1, 1. I'd even probably extend it a little bit more. So then you can put this into your y1, this into your y2. Your values are so small and are so much easier. Let me just show you the difference when you do this trick. So, and this is kind of what I'm going to end up doing each time, so it's worth me explaining it anyway. So I'm going to go y equals, and again, instead of that, what was it, 250,000, I'm going to put 1.2016.11, because here, or not 0.11, sorry. I can't talk and type at the same time, can I? especially when you're dealing with exponentials, the numbers are always large, so, or infinitely small, so it's kind of nice to have another way of doing this, and it's kind of like going, hey, you forgot your equation. Okay, hold on a second. Y equals 1.0093, and this makes it a lot easier in your graphing calculator. Really, Desmos doesn't matter, but you can't use Desmos on those summative assessments, so that's kind of why this is a nice thing to show. Okay, so if you put both of these in your graphing calculator, and now I'm going to have to go back to like the standard screen, so kind of bear with me. I'm sure there's a shortcut to doing this, but so a typical screen, you know, people are going to be at the plus or minus 10, right? All that kind of good stuff, so I'm going to get kind of to that area. There we go. So a standard window in the graphing calculator is about this right here. And notice that really you're looking at that purple line in the purple graph and the orange graph, I don't know which one's which. And the intersection falls right here. And that's just so much easier, lot less window manipulation. So take it or leave it. I'm just showing you a shortcut. It just makes it easier in the graphing calculator, which you definitely need to be able to do or manipulate. So anyway, I'm going to erase this part right here because I need that space for my next problem, which is awesome. It's about a television that cost $1,200 brand new. The value decreases at a 12% rate each year. Now that's not a decay factor, that's a rate, this right here. And we know that this is the initial amount. So it says write an exponential decay model. Well, we have y equals the initial amount, which is 1,200, times, and now this is where people love to write 0.12. They love writing 0.12. But if you put 0.12 there, that means that after the first year, you only have 12% remaining worth of that television. And that is not what you want. You want to go 1 minus 0.12, and that's going to give you 0.88. Raised to, again, I was going to say t because I like saying t because it makes more sense, but I'll put an x there just for consistency. I don't know if you hear that thunder in the rain, it's crazy. Oof. Anyway, okay, so it says estimate the value after 2 years. Well, that's pretty straightforward. Just throw 2 in for x and life is good. Again, just make sure you know how to get it in your calculator and get the correct answer. So I'm putting 2 right in here. And when you calculate that, you'll end up realizing that after 2 years, you have a television that is now worth $929.28. And I've got to tell you that televisions decay a lot faster than that nowadays. But I don't want to miss that whole technological thing that we do. Okay, letter C, this is a graphing one. This is a graphing one. And how do I know that? Because it's talking about the value of the television. When is the value 300? So that is the y value. So we're putting 300 in for y, and we want to know the time it takes to drop down to $300. So I'm going to put 300 equals 1,200, 0.88 raised to the x. And again, now right away you can say, hey, this is going to be my y1, this is my y2, find the intersection and life is good. I am not going to do that because I had said that I use my shortcut that makes it a little bit easier graphing wise. So I'm going to divide both sides by the initial amount to get this 0.88 to the x power by itself. So 1,200 divided by that side, this side, and it sets you up for when we do logs. It's going to be same. You're going to have to know how to do it anyway. So I figured, hey, I'll cut my time here. So 3 over 12. Notice I got rid of my zeros. 3 over 12 is the same thing as 1/4. So 0.25 equals 0.88 raised to the x. So this now is what I would say. Put this into your y1. Oops. This into your y1. This into your y2. And I'm going to show you how to do that in my Desmos program. So I'm going to get rid of these fellows. Oops. And I have y equals 0.25. And then my other equation is y equals 0.88 raised to the x. And again, The windows, what's really nice about this is that, you know, that standard window is -10, 10. So if you hit standard, like zoom standard on your calculator, it'll take you right to this window setting right here. -10, 10 on both the X and Y axis. You'll be able to see the graph instantly without adjusting your windows. And then what you can say is, hey, you know what? I want a little bit more on my X. So looking at this, you'd want to just go up to, like, I don't know, just maybe like X, I would say, goes from -10 to 15 instead of to 10. And you find the intersection and hold it there, and you notice that it takes 10.85 years to reach $300. So it'll decay to $300 in 10.85 years. That's why I was like going, this problem's not really that realistic, because the television might not even last that long. I hate to say that, but okay, so I'm going to get rid of that just for space, and I'm going to say my answer, X equals 10.85 years. And again, a better answer would be, you know, the television will be worth $300 in 10.8 or after 10.85 years. So there it is. Okay, so that's the first part, and I'm going to do half-life, which is a lot, which takes a little time, which is why I'm breaking this video up into two. So get some practice done with the exponential growth and decay actual application problems before, at least that's what I would do, before you start with half-life. Half-life gets a little bit more confusing. Good luck.